Hi everyone. So this video is about the fundamental characteristics of the basic computer. The basic computer is an example computer that is explained in a book titled Computer System Architecture. The author of this book is M. Morris Meno. Before we see what are the key characteristics of this computer, let us first understand the objective of learning about this computer. Whenever we want to know about the internal design of a computer system or various hardware components used by computers or their interconnections or the processing of operands and instructions or programs in a computer, we should always start with a small, simple computing model. And here, the basic computer serves that purpose. So, without unnecessary complexities, if we want to understand how a computer basically is designed and how it works, then the basic computer is one of the best options. So, let us quickly note down the fundamental characteristics of this computer and then we'll move to the hardware configuration of the basic computer. So, as I have said, the main objective of using this computer as an example is its simplicity. It's very simple to design and use. Because of very simple functionalities, the size of this computer is limited. So, it's a very small sized computer compared to any latest computers. It's a general purpose computer. That means a variety of tasks can be performed by this computer and it is not designed for any specific purpose. It is not designed for any specific task. And as it's very simple and small, we can expect a limited number of functionalities from this computer. So these are the key features of the basic computer. Now let us see how this computer is actually designed. To understand the actual internal design, we have to first consider certain hardware components which are required to be organized in a particular manner. Let us start with the memory unit because that is one of the important components, one of the important units for any computing system. So, here, let us assume that the memory unit of the basic computer is of size 4096 cross 16. That means total 4096, 2 raised to 12 memory locations are available in this computer, and each memory location is capable of storing 16 bits of data. Okay, this memory unit is divided into two parts. One part stores the instructions. We can also consider these instructions as programs, and the other part of the memory will store the data or operands. Now, as there are total 4096 locations available in this memory, if we want to uniquely identify a memory location from this configuration, we need to provide 12-bit addresses. So, the basic computer uses 12-bit addresses. So, this is about the memory. Now, let us also understand what will be the format of instructions for this computer and exactly how many bits will be available to depict different parts of an instruction. So, if we talk about the instruction code for the basic computer, then we can assume that one memory word is sufficient to store one computer instruction. That means the size of one instruction would be 16 bits. So the actual bits would be 0 to 15. Now this instruction code will be divided into different parts. For the basic computer, we need mainly three parts to depict uh, the required values for an instruction. So, an instruction usually specifies how to fetch the required operands. Here, for the basic computer, we'll work with an assumption, and that is If we want to perform any binary operation, then one operand will be stored in a special computer register known as the accumulator, abbreviated as AC, and the second operand will be fetched from the memory. Now, if we want to fetch an operand from the memory, we should know the address where that operand is residing. And for that purpose, the first part of the instruction code for the basic computer should have the address information. So here the first part of the instruction code will have a memory address. Now, as we have already decided the size of addresses, the width of any valid address value for this memory configuration, we can easily say that first 12 bits will be occupied to specify addresses. Now, 4 bits are left because a total of 16 bits are available to specify a valid instruction. So, here let us divide this 4 bits into two parts. First three bits in the second part will specify the exact operation to be performed through the instruction. So, operation code, which is also abbreviated as opcode, will be specified in the second part of the instruction. The width of this opcode will be 3 bits. That means bit number 12, 13, and 14 will be available to specify the opcode. The last part of the instruction will specify the addressing mode. This addressing mode will be a single bit value for this computer, and it will be stored in a designated flip flop I. So, I is the name of the flip flop which will be used to store this addressing mode value. Now, let us understand what is the meaning of an addressing mode. So, we have said that the first part of the instruction will have an address. It is not always necessary to have the exact address of the operand readily available in this address part. Sometimes the address of the operand is not known. In that case, some other address will be available in this address part, and the control the system will use some logic to use that available address value to get the actual address of the operand. So, this kind of addressing is known as indirect addressing, because directly the required address, the address of the operand, is not available. So, indirect addressing is quite common in computing systems. The other category of addressing is direct. So, here the actual address of the instruction would be available with the computer, and directly that address can be placed in the first part of the instruction. Now, here for the basic computer, we'll restrict our discussion of addressing modes to only this two. Otherwise, in modern computers, multiple types of different addressing modes are supported. But for the basic computer, we'll consider only direct and indirect addressing. So here we have two options whenever we want to specify an instruction for fetching the operand. So to differentiate between these two, one bit is sufficient, because ultimately we have to write everything in binary if we want to consider the lowest level design. So this last bit, I bit, is reserved for choosing between indirect and direct addressing modes. So for indirect, let us assign the value 1, and if the last bit, the MSB of the 16-bit instruction, is having a 0, then it will be treated as the direct addressing. So this is how the three parts of an instruction are organized in a 16-bit format. Okay. Now, we have already seen what is the accumulator. As I have said, accumulator is a special purpose register available with the computer. So, this accumulator can directly communicate with the adder and logic circuit of a computer system. Whenever the computer is required to perform any arithmetic or logic operations, one of the operands in case of binary operations can be placed in AC, the other operand can be fetched from the memory, and then AC will communicate with the arithmetic unit or logic unit to perform the required operation. By default, the result of any arithmetic or logic operation would go to AC. So, AC will be used as the destination for most of the arithmetic and logic operations in this computer. Now, apart from AC, the basic computer supports seven other registers. So, total eight processor registers are available for the basic computer. Let us just name those registers first, and then we'll see their purposes. So, DR is another important register available in the basic computer. DR stands for data register. Then we have IR, that stands for instruction register. Then we have TR, temporary register. Then PC, program counter. AR, address register. INPR is an input register, and OUTR is the output register of the basic computer. Let us also see the size of all these registers. So DR, data register, is of size 16 bits. IR is also of the same size, and TR is also of 16 bits. So these three registers are of size 16 bits. The purpose of having DR, data register, is to read something from a memory word. Most of the operations in a computer are binary, and to perform binary operations, exactly two operands are needed. So, for the basic computer, for any binary operation, one of the operands can be kept in AC, and the other operand is to be fetched from the memory. Now, memory and AC cannot communicate directly. So, first, before using the content of a memory word as an operand, you have to read that value into the data register DR. So, that is the basic purpose of having this 16-bit register in the basic computer's configuration. The next 16-bit register is IR. So, as the name suggests, this is an instruction register, and it is used to store instructions which are to be executed in the next clock cycle. So, for example, you want to perform the addition operation on the content of AC and a memory word. For that, the basic computer has one instruction named add. So, if the control is required to execute that add instruction, it is first required to be placed in the instruction register. After placing that instruction in IR, the control can decode the meaning of that instruction and can perform the required task. So, holding the instruction which are to be executed next is the objective of having IR in the basic computer. The next register is TR. It is again a 16-bit register. The name is temporary register, and whenever you have some intermediate values to store, be it intermediate operands or results, you can always use TR. Okay, next two registers are PC and AR, program counter and AR. These two registers are of size 12 bits. So the purpose of the address register, as the name suggests, is to hold address values, addresses of the memory words. So it's a 12-bit address register because the memory unit of the basic computer needs 12-bit addresses. So AR is directly connected with the memory unit because whenever you want to access memory for reading something from the memory or writing something into the memory unit, you have to provide the address, and that address will always be passed through this AR, and that's why AR and memory unit can directly communicate. They have a direct connection available between them. Uh, Next 12-bit register is PC, the program counter. So program counter basically points to an instruction which is to be executed next. For example, you have a series of instructions available in your program. Currently, the control is executing the first instruction. If you follow the sequential execution, then after the first instruction, the second instruction should be executed. So, this is the responsibility of the program counter to point to the next instruction in sequence. So, if the control is currently executing the first instruction, the content of PC should be the address of the next instruction in the sequence. And every time, if you follow the sequential execution in the basic computer, then to point to the next sequential instruction, PC can be incremented by 1. And that's why this program counter is actually a register, but it has the counting capability, and the name program counter is assigned to this particular register. So it's a register, it can hold values, and at the same time it can also count, uh, it can also increment the existing content of it. Okay, after this we have two more registers available in the basic computer. These registers are INPR and OUTR. Now the size of these two registers are 8 bits. These two are special purpose registers. As the name suggests, INPR, the input register, is used to get input values from the externally connected input devices. Different types of input or output, which are known as peripheral devices, can be connected to a computer. So, for the basic computer, also, there are certain types of input devices that you can connect to it. So, here for INPR, if you want to read an input value from the connected input device, then you can transfer the input data and 8-bit alphanumeric data to INPR, and through INPR that value can be passed to the accumulator AC register for further processing. Similarly, if you consider the reverse direction, that means your computer has generated some output value, some resultant value, and you want to forward that value to the connected output device, then you can use the OUTR register. That means most of the times the result of any data manipulation would be available in AC. From AC, you can transfer that content to this output register, and then through this output register, the connected output device will receive that output data. So that is the purpose of OUTR. So total 8 registers are available in the configuration. 4 16-bit registers, AC, DR, IR, TR, then two 12-bit registers for holding the address values PC and AR, and two 8-bit registers INPR and OUTR. So 8 processor registers and one memory unit of size 4096 cross 16. These are the most important hardware components to consider for the basic computer. Now let us see how this registers and the memory unit are connected with each other, because most of the times the registers and the memory unit need to communicate with one another, and for that some actual physical paths must be available between them. So for that we can consider the concept of a common bus system. So let us see how a common bus system can be designed for this computer, specifically for the basic computer. So, to design this common bus, we can either use three state buffers or multiplexers, because the basic purpose is to select a particular source register from which the content can be transferred to one or more destination registers. Here we'll treat memory unit as a similar entity to a register, because memory and register, these two are mostly involved in most of the transfer processes. Okay, so if we want to understand the actual configuration of this common bus system, we need to understand how many options we have for making the selection. What can be selected as the source? If you want to understand that, you have to just list down the total number of entities available. So here we have total 8 registers and one memory unit. So total 9 entities are available for selection. Now, the actual bus of the basic computer does not involve all 9 entities, because certain registers of the basic computer have specific purposes. So here, instead of considering 9 entities for designing the bus, we'll consider only 8. The reason is, as we have seen, INPR, the input register, is used to read an input value from the connected input device. Now, this register uh, is actually not required to communicate with all the processor registers or the memory unit except AC. So INPR communicates only with the accumulator in the basic computer. This register is not required to communicate with any other processor register or the memory unit of the computer. That's why we can exclude INPR from the common bus configuration. So if we exclude INPR and consider the total count, then we have now 7 registers and 1 memory, total 8 entities. Now, if we want to design a common bus that will select any one entity out of this 8 and use that as the source, then we have to use a certain number of multiplexers. You can also use 3-state buffers. Basically, 3-state buffers can replace multiplexers in the design. So let us first try to find how many multiplexers are needed, and then what would be the size of each multiplexer. So now, to decide the number of multiplexers, you have to decide maximum how many bits you want to transfer through the bus. So, if you recall the size of various processor registers in the common bus, you have total 4 16-bit registers, right? And for the memory unit also, the size of one memory word is 16 bits. So maximum 16 bits will be required to transfer via the common bus. So if we are implementing this bus using multiplexers, that means one multiplexer will be able to generate one bit of output data. So, to facilitate the parallel transfer of 16 bits, simultaneous transfer of all 16 bits, then you need to use 16 multiplexers. So, the number of multiplexers to be used to design the common bus is 16. Now, let us also decide the size of the multiplexers. So for that, you have to consider how many options you have for making the selection. As we have determined that count, total 8 entities are available, and at any time one of these entities will act as the source. Okay, so out of 8 we choose exactly one for transferring its content via the common bus. So we need to use 8 cross 1 multiplexers. The 8 options, the 8 entities from which you have to choose exactly one as the source entity, uh, for that the size would be sufficient, 8 cross 1. Those entities should be connected as the source to this 8 cross 1 multiplexers. Okay, So this is how a 16-bit common bus for the basic computer is to be designed. There are 16 bus lines, so it makes 16 bits of data can be transferred from one location to another, from source to destination. Now, as we are using 8 cross 1 multiplexers for implementing the 16-bit bus, we obviously require three selection lines. So let us call them S2, S1, and S0. So, depending on certain combinations of the selection lines, a particular entity will be selected as the source. So, we'll see what values are assigned to the selection line variables. But before that, we have to understand how processor registers or the memory unit of the basic computer will communicate with the bus. So let us just write the names of the eight entities we have decided to consider for the bus: memory, AR, PC, DR, AC. INPR will not be a part of the bus, but as INPR is required to communicate with the AC, we will just write its name here. Then we have IR and then TR, and lastly outer. Okay. Now, most of these entities will be connected to the bus. That means they can place their content onto the bus lines. Similarly, if we consider the other direction of transfer, source to bus and then bus to destination, then most of these entities will also receive the content from the common bus. Okay, so for the memory, two operations are possible: read and write. And memory will always receive the address input from the address register. Memory can receive the input from the bus, and memory unit can also place its content onto the bus lines. So, read and write are the control inputs from the memory, and memory can communicate with the bus in both the directions. Then address register AR can also communicate with the bus in both the directions. That means AR will receive inputs from the bus, and AR can also transfer its content to the common bus. The same is the case with PC. In both the directions, the transfer is possible. Same for DR. AC can place its content onto the bus, but it will not receive any input from the bus lines. We'll see how AC will receive the inputs, but let us first see what is the direction of transfer possible for the remaining registers. As I have told you, INPR communicates only with AC. So obviously it will not receive anything from the bus, and it will not place its content on the bus lines. So INPR is actually the only register in this configuration that is not communicating with the bus. Then IR, again, in both the directions, the information can be transferred for the instruction register. For temporary register also, you can transfer its content to the bus. Similarly, TR can receive inputs from the bus. And out R, the purpose of out R is to receive something from AC and then forward that value to the connected output device. So out R will only receive the input from the bus. It will never place its content on the bus because out R is not required to give its data, give its content to any of these processor registers or the memory unit. It is simply required to communicate with the connected output device, and output devices or input devices are external devices, peripheral devices, not a part of a computer, and that's why will not show the transfer path from out R to any output device. Okay, so the directions are depicted in this diagram. Okay, now let us see how AC receives the inputs. As I have told you in the beginning of this session, most of the arithmetic and logic operations involve the accumulator, the AC register, and that's why there should be a direct connection between the adder and logic circuit and the accumulator. So, most of the arithmetic and logic operations are binary, and that's why AC is used as one of the operands for performing those operations, and the other operand mostly comes from the memory. Now, as we know, the content of a memory word cannot be directly used for manipulation. The memory word is first fetched in the data register DR, and then that data register's content is used by the adder and logic circuit to perform the required operation. Now, unary operations are also possible for most of the computers. So, for the basic computer, also, if any unary operation, that means the operation that needs only one operand, is to be executed, then the content of AC can be used. In that case, no memory word is required to be accessed, no need to use even the data register. The content of AC will be used as the operand, and the result of the operation will also go to AC. So here the concept is from adder and logic circuit, the accumulator register receives the input. And as I have told you, INPR register communicates with the AC, so that value also goes through the arithmetic and logic circuit. So the direct path between INPR and AC is not available. If you want to transfer INPR to AC, you have to complete this transfer via the adder and logic circuit. So the adder and logic circuit has three inputs. One is DR, second input is AC, and the third input is INPR. And the result of this adder and logic circuit directly goes to AC. Now, sometimes for some arithmetic operations, an additional bit is also generated after the execution. So, to hold that additional resultant bit, adder and logic circuit uses a designated flip flop named E. So, E stands for extended AC. So, if any additional bit gets generated as the result of the selected operation, the arithmetic and logic circuit will forward that value to E. So, this is how AC receives input from the adder and logic circuit. And the advantage of not connecting the common bus lines to the input pins of AC is that you can swap DR and AC in the same clock cycle. So here you have to consider that if you are transferring something using the common bus, then it will take approximately one clock cycle of time. So from source to destination, that transfer will be completed approximately in one clock cycle. So, if you want to exchange the content of AC and DR, whatever is available in DR, you want to transfer it to AC, and the content of AC you want to send to DR. Then, for this two transfers, one clock cycle is sufficient if you consider this configuration. So, how that can be done? The content of DR can be transferred to AC by selecting the transfer operation in this adder and logic circuit. So, that does not actually involve the common bus. If you want to transfer the content of AC to DR, then you have to simply place the content of AC onto the bus lines, and via bus, the data register will receive that value. So one transfer involves the bus and the other transfer involves the adder and logic circuit. That's why there is no conflict in accessing the bus. Note that two transfer operations cannot be completed except this two in this common bus configuration. For example, you want to transfer the content of PC to AR, and at the same time you want to transfer the content of data register to temporary register, DR to TR. So these two transfers cannot take place in the same clock cycle. PC to AR will happen during the selected clock cycle. If you select this transfer as the first transfer, you can initiate the second transfer only after the completion of this transfer, PC to AR, because both these transfer operations will need the common bus, and at a time the common bus can have the content of only one source register. That's why except this two, no other transfer can take place simultaneously in this common bus configuration. Okay, now let me also tell you what are the control inputs available for all these registers. So for most of the registers, we need to frequently execute certain operations like load, increment, and clear. So most of the registers will have these three control inputs. So if you want to load any of these registers by a new value, then you can simply enable this input by setting it to 1. Similarly, if you want to increment the content of a processor register, you can enable this input pin. You don't have to use the adder and logic circuit to add 1 to the existing content. And clear means all the bits will be cleared to 0. So clear, increment, and load can be directly executed on most of these processor registers by simply enabling the respective control input pins. Okay, so AR will have all three control inputs, PC will also have all three control inputs, DR and AC will also have load, increment, and clear. As INPR is actually not a part of this configuration, it will not have any of this control inputs. And it also makes sense. You cannot load INPR based on the clock of your computer, because INPR will be loaded with some input value when the externally connected input device will send some data. So you cannot control the load operation of INPR in this configuration. For that, you need a different design. Similarly, whatever input value is available in INPR should not be incremented. It does not make any logical sense to just increment the existing input value. And clear. Again, the content of INPR is not required to be cleared. It is always overwritten by the new values. So these three control inputs are not available for INPR. Next register is IR. So for IR, the basic purpose is to load instructions which are to be executed. So for IR, there is only one control input available, and that is load. Instruction codes are not required to be incremented. Similarly, clear is also not a useful operation for IR, and that's why it is not available. So IR has only one control input, load. Then TR, it has all three control inputs, and out R. Now, the out R register is used to read the resultant value from the accumulator. So for out R also, only load control input is available. It does not make sense if you try to increment the output value by 1, because the final output is already generated. Out R is just having that output value so that it can be connected to the peripheral device, can be forwarded to the peripheral device. That's why increment is not needed, and clear is also not required to be used for out R, and that's why that control input is also missing for out R. So IR and out R, these two registers have only load control input. INPR does not have any control input. And except INPR, all other registers will have a common clock pulse, because registers are sequential components, clock driven devices, and that's why they need a clock pulse to change their state. Registers are basically consisting of a series of flip flops, and to change the state of a flip flop, you have to provide the clock. Okay, so this is about the control inputs. Now, let me also tell you how to select a particular register as the source in this configuration. So for that, as we have decided, this three selection variables will be used to choose a particular entity as the source. So let me just write the decimal equivalent of the binary combination that you will need to select a particular entity as the source. So for memory, this selection in decimal would be 7. That means if you set S2, S1, S0 as 111, that is 7 in decimal, then memory will be selected as the source. Similarly, for AR, you will use the decimal value 1. That means if you set 001 as the selection line combination, then AR will be selected as the source. For PC, this number is 2. For DR, it's 3. For AC, it's 4. INPR is not required to be considered. For IR, it's 5. And TR is 6. Note that we are not required to assign any selection line combination to out R, because out R is not connected to the bus for placing its content. Out R does not forward its data to the bus. And that's why out R does not have any selection line combination. So if you have three selection lines, three bit combinations, if you try to generate, there will be total 8 possibilities. Out of those 8, 7 combinations will be used here, 7 for memory and 1 to 6 for the processor registers, and one combination 0 will remain unused, so it can be used for a future purpose. Okay, so this is about the common bus system and the transfer of information in the basic computer. Now, let us see what happens to an instruction when it is fetched for the execution. So for that, we have to understand how the control in the basic computer interprets the meaning. So let us again see the instruction format. Total 16 bits are available. The first part is the address. The second part is the opcode, and the last bit is the addressing mode bit, which will ultimately go to a flip flop I. Okay, so when this instruction is placed in the instruction register for execution, the control is first required to interpret the meaning of the instruction, because the control has to know what is exactly required to be done through the given instruction. For that, this opcode part is to be decoded, and this decoding can be done using a 3x8 decoder. This 3x8 decoder will be available in the control unit of the basic computer. There are two ways to design a control unit for any computer, hardwired and microprogrammed. So this control unit is hardwired. Whatever logic the control unit follows is hard coded using actual hardware components. This control unit is designed, and that's why it is known as hardwired control. So using this 3x8 decoder, the control will decode the 3 bits of the opcode, bit 12, 13 and 14, and can generate a total of 8 outputs. So this outputs will be D0 to D7. So depending on the opcode combination, exactly one of these 8 outputs will be 1. So for example, if your opcode is 101, then D5 will be 1 and rest of the decoder outputs will be zeros. So this is how the control determines the exact operation, by looking at the opcode part, by decoding that opcode part. This is the addressing mode bit. So the control will use this addressing mode to determine how to fetch the operand. If it is indirect addressing mode, then the control has the address of the effective address. So effective address is nothing but the actual address of the operand. So in case of direct addressing, directly the effective address will be available in the address part. In case of indirect addressing, address of the effective address will be available here in the address part. Okay. Now this address part, which is of size 12 bits, will be directly used by the control unit to process it, and using that processed address, the memory unit will be accessed to read the operand's value. So this is the responsibility of the control unit to find the addressing mode, to find the exact meaning of the instruction, and to use the actual addresses to read the operands from the memory. Okay, now whatever processes are to be done by the control unit must be executed, must be performed at certain times. So, along with some other control conditions, the control unit also uses a set of timing signals. So, timing signals basically specify at what time what should happen, and control conditions are different other variables which can tell the computer that if certain condition becomes true, then execute something if the given timing signal is one. So, for example, here this decoder outputs can be treated as control conditions. Along with this decoder outputs, you can use different timing signals. Now, the question is how these timing signals are generated. So, the control unit of the basic computer uses a 4-bit sequence counter to generate a series of timing signals. So this is like a normal counter. With every clock pulse, the sequence counter's value is incremented by 1. Uh, the count sequence would be 0002 1111, as this is a 4-bit counter. And if we want to generate timing signals based on this count sequence or count values, then we have to connect this sequence counter to a 4x16 decoder. So whatever is the count value generated by the sequence counter is given to this 4x16 decoder. So based on 4-bit count values, this decoding will take place. For a 4-bit count value, this decoder will generate a total of 16 outputs. And these outputs can be labeled as T0 to T15. And this decoder outputs can directly be used as timing signals. So, one example of a control function that uses the 3x8 decoder output, let's say D3, and a timing signal T5 can be given like this. So, this means a condition, a control condition, that is when T5 timing signal is generated and the decoder of the 3 cross and the output of the 3 cross 8 decoder is D3, then execute this operation, execute the associated micro operation. So here I have just taken some random example. Let's say we want to transfer the content of PC to AR, and this transfer should take place only when T5 timing signal is 1 and D3 is also 1. So this is how you can combine decoder output and timing signal to form the control function, and this control function will control the execution of the associated micro operation. After generating all 16 timing signals with each clock pulse, this decoder will generate one timing signal. So if your count sequence is, let's say, 0000, count value is 0000, then the output of this 4x16 decoder will be T0. You have to apply a clock to this counter. So when the next clock pulse is triggered, the next count value is generated, that is 0001, and this corresponds to T1 as the decoder output. So this is how a series of timing signals can be generated in the control unit. So when the last count value occurs, that is 1111, at that time the control generates T15 timing signal, and after that the counter is reset. So it will again start counting from 0000, and it will again generate a sequence of 16 timing signals T0 through T15. So this is how this counter is designed. Okay, so this is about the control unit. Now, let us understand how instructions are actually executed in the basic computer. So, for that, we have to understand the instruction cycle execution. Instruction cycle is nothing but a series of phases through which your instruction should go. So, for the basic computer, there are four phases of the instruction cycle: fetch, decode, reading the effective address, and actual execute. So, initially, instructions are available in the memory. If you want to execute an instruction, you have to fetch it in the instruction register IR. So initially, PC will have the address of the instruction to be executed. Now, this address is required to be given to the memory unit so that whatever instruction is available at that address can be read in IR. Now, PC cannot provide any address value directly to the memory unit. You have to first transfer that value to AR, and this happens at time T0. So, T0 can be treated as the control function for this transfer. Now, once this address is available with the AR, using this address, the memory word can be accessed, and the content of this memory word can be given to IR. Now, the purpose of PR is already served for the current instruction. So now it should point to the next sequential instruction, and for that you have to simply increment PC by 1. And this two processes happen simultaneously at time T1. So these two operations are associated with the fetch phase. Now let us see what happens in the next phase, that is the decode phase. Now the instruction is available in the IR. So the control unit will try to decode the meaning of this instruction using that 3x8 decoder available in the control unit. So IR of 12, 13, and 14. These three bits will be treated as the opcode, and decoding process will be performed on those three bits. The possible outcome of this decode process would be any decoder output from D0 to D7 as 1 and rest of the outputs as zeros. Okay, now what happens with the address part? So, along with this decoding, the control transfers the address part of the instruction register to AR, because addresses are always to be processed through AR. And the last bit of IR, that is bit number 15, is used as the addressing mode bit. And as we have seen before, this bit always gets stored in a designated flip flop I. Okay, so this three operations will take place simultaneously at time T2 to complete the decode phase. Now, reading the effective address. Uh, in case of indirect addressing, the control is required to first get the effective address. Remember that effective address is the actual address of the operand. So, if the effective address is not readily available in the address part of the instruction, then the control has to first get the effective address. So that processing is needed as the third phase. And lastly, depending on the given instruction's nature, the actual execution will be performed. So now let us understand what types of instructions are supported by the basic computer. So basic computers instructions are mainly divided into three categories. First is memory reference instructions, second is register reference, and the third is IO instructions. So, as the name suggests, memory reference instructions always access a memory location to get the operand's value. So, wherever memory is involved, that instruction is called a memory reference instruction. Register reference instruction means the memory is not required to be accessed. The content of a processor register is to be used as the operand. And IO instructions are mainly used to communicate with the input output devices. Now, these three are the categories of instructions, and now we'll see how many memory reference or register reference or IO instructions can be defined for the basic computer. For that, first we need to decide how this instructions will be differentiated. So, opcode is the main part that defines the type or exact name of the instruction. So, as we know, for the basic computer, three bits are available: bit number 12, 13, and 14 for specifying the operand. Now, if you consider three bits in binary, then eight combinations are possible. Out of these eight combinations, let us choose the last combination, that is 111. So first we want to differentiate between memory reference and other type of instructions. So if your opcode is 111, it can be either register reference or IO instruction, but certainly not a memory reference instruction. So out of 8, we have used this combination to denote either register reference or IO instructions. So the remaining 7 combinations, that is from 000 to 110, these 7 combinations can be used to depict any memory reference instruction. Now, as both register reference and IO use the same opcode, you should have some logic using which particular instruction can be found out. So, to differentiate between register reference and IO, you can use the last bit. Note that register reference or IO instructions do not need to access any memory location. So, the concept of addressing mode bit is useless for register reference or IO. So this last bit you can use to differentiate between these two types of instructions. So let us fix this for the basic computer. If MSB is 0 and opcode is 111, then it is clearly a register reference instruction. So for the other value of MSB, that is 1, if the opcode is 111, that then it shows an IO instruction. So last 4 bits are ones, then it is an IO instruction. Last 4 bits are 0 1 1 1, then it's a register reference instruction. For memory reference, you need to use the MSB bit number 15 to understand the addressing mode. So it can be either 0 or 1 depending on the actual given operands. And the first part will specify some address in case of memory reference. For register reference and IO, you do not need to have memory references, memory addresses in the first part. So for register reference, the first part, bit number 0 to 11, can specify a unique register ID, because if your operand is not available in the memory unit, it must be fetched from some register. And multiple registers are available usually in any computer. You need to particularly specify what register is to be used for fetching the operand, and for that you need a unique register identifier. So instead of a memory address, in case of register reference instruction, you can have a register identifier. Similarly, for IO, the memory unit is not required to be accessed. That's why we do not need actual addresses. But if you want to communicate certain connected input or output devices, you should know what is their identifier. Again, these identifiers are required to be unique. So, in case of IO instructions, the first part should have a unique identifier of some input or output device. So this is how instruction code format will have different values in the basic computer depending on the exact type of the instruction. Now let us see some instructions which we can include in the instruction set of the basic computer. So for the memory reference category, let us include 7 instructions. The names of these instructions are AND, add, load, store, bun, that is branch unconditionally, BSA, branch and save return address, and ISZ, increment and skip if 0. So the hexadecimal codes for these instructions would be okay. So for memory reference instructions, you know that I, the last bit, addressing mode bit, can be either 0 or 1. So if I is 0, and if you consider a 16-bit binary combination, then first 12 bits would be the address values, actual address values, which cannot be predefined. It will depend on the actual execution, actual addresses of the operands. So if we want to represent those 16-bit instructions to into 4 digit hexadecimal codes, then we can write something like this. But before doing that, we have to fix the opcodes of all these instructions. So for AND, the opcode is 000. For add, it is 001. Load, load accumulator, it has 010 as the opcode. 011 opcode is assigned to store AC instruction. Bun, branch unconditionally, will use 100 as the opcode. 101 is assigned to BSA, and 110 to ISZ. This is the permissible range of opcodes available for the memory reference instructions. Now, so this will be bit number 12, 13, and 14, and addressing mode will be the last bit. So you need total 4 hexadecimal digits to accommodate a group of 4 bits in each. Okay, so last hexadecimal digit can be decided like this. Opcodes are fixed and I can be 0 or 1. So if you consider I as 0, you will have 4-bit combinations like 0000, 00001, 0010, 0011, 0100, 0101, and 0110. Okay, now if you convert this 4-bit binary values to hexadecimal, you'll end up with this. 4 zeros is 0 in hexadecimal. Then if we consider this 0100 is 4 in hexadecimal, and likewise. And this XXX represent the actual address value for the first 12 bits because they cannot be predetermined. Okay. Now, if we consider I as 1, then how these combinations will change? They will have 1 0 0 0, 1 0 0 1, 1 0 1 0, and so on. So basically, instead of zeros, I is required to be 1. So in that case, you will get 8, 9, A, B, C, D, and E as the last hexadecimal digit. Again, addresses cannot be determined, so first three hex digits, which correspond to first 12 binary digits, will be XXX, some actual address values. So this is how the hexadecimal codes of memory reference instructions are decided. Now, if we consider the second category of instructions, that is register reference, then the opcode is fixed, that is 111, and MSB is also fixed, that is 0. Now, if we try to represent this 4-bit binary to an hexadecimal value, it corresponds to 7. So, the last hex digit for any register reference instruction would be 7. Let us first write the names of the register reference instructions that the basic computer supports. Okay, so let us quickly write the hexadecimal codes for these instructions, and we'll also see what is the name and meaning of these instructions. So CLA is clear accumulator. The hexadecimal code for this is 7800. CLA is clear the extended AC flip-flop. The hex code for this instruction is fixed 7400. CMA is complement AC. 7200 is the code. CMA is complement AC, and CME is complement E flip flop with code 7100. CIR is circular shift right. For that, the code is 7080. CIL is circular left shift, obviously on AC. INC is increment AC with the code 7020. SPA is a skip instruction. So if the AC is positive, then skip the next instruction in sequence. For that, you can use this code. SNA is similar to SPA, but here AC is required to be negative to skip the next instruction in sequence. So this uses this code. SZA has 7004 as the hex code. If AC is 0, then the next instruction will be skipped. And SZE will depend on the content of extended AC flip flop, E flip flop. So if E is 0, then PC will be incremented by 1 to skip the next instruction in sequence. And the last is the halt instruction, a special instruction that basically stops everything in a computer. All the execution processes are suspended. So for that, this is the hexadecimal code. Now let us see how many IO instructions are available and what are their hexadecimal codes. Okay, so input instruction. INPR to AC. If you want to facilitate this transfer, you can execute input instruction with this code. So how F is obtained? We know that opcode is 111 and the last bit is also 1 for any IO instruction. So this corresponds to F in hexadecimal. Out instruction has this code. Out instruction is used to transfer the content of AC to out R. SKI is again a skip instruction. So if an input flag FGI is having a certain value, then PC is incremented by 1. So SKI is having the code F200. SKO has this code. So skip on output flag. So FGO is again a flag available in the IO configuration of the basic computer. So based on the value of FGO, you can increment PC by 1. ION is for enabling the interrupt on. The code is this, and F040 is the code for I off, interrupt off. Okay, now you might be wondering how the first three hexadecimal digits are determined for register reference and IO instructions. So here we have multiple options. If you consider the instruction code format again, then you have total 12 bits, first 12 bits for specifying register identifiers. So you can make total 2 raised to 12 combinations. Out of this 2 raised to 12, you can use any 12 because total 12 register reference instructions are available for the basic computer. So we have decided to keep it very simple, and at a time, out of this 12 bits, we want to use exactly one bit as 1 and rest of the bits as zeros. So if you consider 800 and you convert it into binary, then 8 corresponds to 1000, 0 is all four zeros, and again for 0, we can have the same binary combination. So exactly one bit is 1 out of this 12, and rest of the bits are zeros. So bit number 11, we are counting the bit positions from 0. So 0 to 11, total 12 bits. So bit at position 11 is 1 for CLA. Similarly, if you consider 400, then this would be 0100, and for rest of the digits there will be all zeros. So bit number 10 will have a 1, rest of the bit positions will have zeros. So we have used this combinations out of 2 raised to 12 possible combinations to make our combinations very simple. At a particular significant bit position, there will be a 1, rest of the bits will be zeros. And the same logic is followed for the IO instructions as well. Okay, so we have seen the total instructions that the basic computer supports. 7 plus 12 register reference instructions and 6 IO instructions, total 25 instructions. You can add more instructions to the basic computer based on your requirement. But currently, we'll limit our discussion to only 25 instructions. Okay, now let us see what happens after the after the decode phase. We have already seen the fetch phase and the decode phase. Let's see what happens in the third phase. Third phase is the effective address reading phase. Now, this address is required to be used only if the given instruction is a memory reference instruction, because as we have just seen, for a register reference or IO, you don't have to access the memory you need particularly. So, during this third phase, before reading the effective address, the control determines the type of the instruction. So, for that, certain combinations can be used by the system. So, now we know the opcode range or fixed opcode values for the three types of instructions. So, if D7 is the output of the 3 cross 8 decoder available in the control unit. So, if that decoder generates D7 as the output, that means the opcode must be 111. So, in that case, the instruction can be either register reference or IO, but it cannot be a memory reference instruction. After looking at uh, the decoder output value, the control looks at the last bit, the I bit, the addressing mode bit. If D7 is 1 and I is 0, that means it is clearly a register reference instruction. If I is 1 and D7 is also 1, then it is clearly an IO instruction. So if D7 is not 1, In that case, it must be a memory reference instruction. So this is how control functions are determined for the three types of the instructions. D7 is 1, I is also 1, and timing signal is T3. This T3 timing signal actually corresponds to the third phase of instruction cycle. So this will be an IO instruction. Now for IO instruction, no address is required to be fetched, so the control can directly execute the IO instruction. It is not required to read any effective address. Similarly, if D7 is 1 but I is 0 and time is T3, then the instruction is clearly a register reference. Here also no need to read the effective address, so the control can directly start the execution. Now, if D7 is not 1, then it is clearly a memory reference instruction. In that case, the control needs to look at the value of the addressing mode. If I is 0 and D7 is not 1, then it is a direct memory reference instruction. So here also the effective address is not required to be calculated because the effective address is already available in the address part. So nothing will happen during this T3 timing signal. By the way, the duration of each timing signal is also approximately one clock cycle. Now, if D7 is not 1, that means a memory reference instruction, but I is 1, that means an indirect memory reference instruction, and time is T3. So, here the control is required to read the effective address because the address part currently specifies the address of the effective address. So, to do that, whatever is the address value available in the instruction, the control has to go to that location and read the address stored at that location in AR. So this is how the third phase of the instruction cycle gets executed. Now, fourth phase is the actual execute phase. This phase is needed uh, to be started from time T4 only for memory reference instructions. Because for register reference and IO instructions in the basic computer, one clock cycle is enough to complete the execution. So at time T3, both register reference or IO instructions can complete their whole instruction cycles. So T4 timing signal is needed only if you have memory reference instructions. So this is how the instruction cycle of the basic computer is determined. So in the next session, we'll see exactly how the memory reference instructions of the basic computer can be executed. What will be the exact micro operations to be executed to perform a certain memory reference instructions task.